Good evening, my dear students. This is the second lecture on mathematical expectation 2. So, in the previous lecture, we have learned about the conditional mean, conditional variance, and different topics of conditional distribution. Now, in this lecture, we mainly focus on regression curves. So, what do you mean by regression? Regression is a statistical method, actually. All the people of statistics are known about the regression. So, this is used in finance, investing, management, economics, everywhere you can find, and other disciplines that attempts to determine the strength and character of the relationship between one dependent variable, mainly that is symbolized as y, and series of other variables known as independent variables. So we can say in compact form, in statistical modeling, regression analysis is a set of statistical process for estimating the relationship between a dependent variable and one or more independent variables. So let's start the topic. So first I will describe what is the regression curves. So for a continuous distribution, as we are discussing about the curves, we will consider the continuous distribution. So for continuous distribution, the conditional mean myx is sometimes called the regression function of y on x. So what is your myx? Already we have discussed in the previous lecture. Your myx is given by, it's a conditional mean. Your numerator will be minus infinity to infinity y, and the joint PDF fxy of a continuous distribution dy, and the denominator will be fxx, that is marginal density functions. That is marginal density function of x. Okay, that is marginal density function of x. So for a continuous distribution, the conditional mean myx, already I have explained this, is sometimes called the regression function of y on x. So this conditional mean is known as the regression function of y on x. And the expression is this. And the curve y equal to myx, the curve y equal to myx, where myx is the regression function of y on x, or it is known as conditional mean. Actually, the background of regression function is the conditional mean. It's called the regression curve of y on x. So this is your regression curve of y on x. Similarly, you can define a regression curve on x on y will be x mxy. So mxy is the conditional mean of x on the condition that y. So your denominator will be fyy in this case, right? It's a density function. So you can write the conditional mean as minus infinity to infinity x and the joint density function fxy dx by the marginal density function fyy, right? So this is your conditional mean, and we have explained regression curve of y on x and regression curve of x on y. So this is number 1 and this is number 2. Now next, some important observations for your concept. We notice that if you write expectation of m1 myx, where myx is the regression curve of y on x, regression function of y on x, or conditional mean myx, that is equal to minus infinity to infinity myx fxx dx. That is from the definition of the expectation. And also myx, if you replace the values of myx by this integration, this value, because the expression of m1 myx is minus infinity to infinity y fxy, the joint density function of x and y, if x and y are two random variables, dy and fxx. So if you write this, so you will have this expression finally. Fxx got cancelled and you are remain with this expression y fxy dx dy, which implies that, and this is nothing but your my, mean of y. This is nothing but your mean of y, right? So which implies that myx is nothing but your my, which can be written as my, mean of y. So hence sigma squared myx, if you take sigma square, that is the variance, that is equal to expectation of curly bracket myx minus my whole square. That is, variance is the measures of dispersion, deviation from the mean. It gives you the measures of dispersion that gives you deviation from the mean. So this gives a measure of deviation of the regression curve. So actual concept is that this gives a measure of deviation of the regression curve y equal to myx from the horizontal line y equal to my. Okay, from the horizontal line y equal to my. So this gives a measure of dispersion or measure of deviation of the regression curve. The regression curve is y equal to myx from the horizontal line this. So that is first important observation. Next, we know that the conditional variance sigma square yx is a measure of dispersion of the conditional distribution of y on the hypothesis x equal to x. Just like mean you have calculated, it's a conditional mean myx on the hypothesis x equal to x. Similarly, we can define conditional variance sigma square yx conditional for the conditional distribution of y on the hypothesis x equal to x, and hence that of the two-dimensional mass distribution lying in the infinitesimal vertical strip between x and x plus dx about the conditional mean myx for a fixed value of x. So that gives the significance of conditional variance sigma square yx. Now we can write expectation of sigma square yx as, just using the definition of expectation, integration minus infinity to infinity sigma square yx fxx dx, and replacing the value of sigma square yx as y minus myx, where myx is the conditional mean. And if you replace the sigma square expression for sigma square, you will have this expression lastly. So which implies that expectation of sigma square yx is nothing but equal to expectation of y minus myx whole square, which is in general different from sigma square y and gives a measures of dispersion of the bivariate distribution about the regression curve y equal to myx. So expectation of sigma square yx gives the measures of dispersion. how far the data deviate of the bivariate distribution about the regression curve y equal to myx. This is called the variance of y about the regression function of y on x, and denoted by sigma square xy, and denoted by sigma square xy. That is, sigma square xy is expectation of y minus myx whole square, and this is called the variance of y about the regression function of y on x, about the regression function of y on x. Similarly, you can define sigma square yx, that will be variance of x about the regression curve of x, about the regression function of x on y. Okay. Next, so I will state without any proof a very important theorem. For any continuous function gx, expectation of y minus gx whole squared is minimum when gx is equal to myx, conditional mean. So if I draw a curve, suppose this is x-axis, y-axis, okay, and this is the curve, suppose continuous curve y equal to gx, and the data actually scattered around this curve, and suppose one of the point is xy. So this, you can measure the vertical strip, you can measure the vertical distance from the curve. So this is the vertical deviation, this is your y minus gx. So you can have another point x1, this is x1 y1, another point suppose x0 y0, so you can measure the deviation again. Another point x3 y3, you can measure the vertical deviation, and the point can be below also. So the distance can be negative, the difference can be negative or positive. That is why you have taken a square. That is the significance. So for any continuous function gx, expectation of y minus gx whole square is minimum when gx is actually taken as myx, the conditional mean of y on x. So what is the geometrical interpretation? So here y equal to gx represent any continuous curve, and expectation of y minus gx square is the mean value of the square of the deviation of the distribution from the curve. You are taking the square of the deviation of the distribution from the curve, mean value, and expectation means their mean value measured in the direction of the y-axis, which is thus a measure of dispersion about the curve y equal to gx. Now the theorem states that among all continuous curves, this mean value is minimum for the regression curve y equal to myx. Hence, among all continuous curve, the one which minimizes the mean value of the square of the deviation in the direction of the y-axis is the regression curve of y on x. So your conclusion is very, very important. Among all continuous curves, you can consider any infinite number of curves, the one which minimizes the mean value of the square of the deviation in the direction of the y-axis is the regression curve of y on x. So that's the diagrammatic representation, and the values can be scattered like this. This is the values, the bivariate data. Your data can be scattered like this, but you have taken a point xy, and this vertical deviation is y minus gx. This is the curve y equal to gx. So you have to consider that curve. You can consider infinite number of curves through the data. You can draw. This is your, all the points are actually bivariate data, x1 y1, x2 y2, x3 y3. So you have to choose a curve, the one which minimizes the mean value of the square of the deviation in the direction of the y-axis, is the regression curve of y on x. Now next point is another important point. If x and y are independent, if they are not dependent, so I am talking about a bivariate data. If x and y are independent, they are not dependent on each other, then the regression curve of y on x is y equal to my, which is a straight line parallel to the x-axis. So if your data is independent, you will have y equal to my. This is your y equal to my line, which is parallel to x-axis. And the regression curve of x on y is x equal to mx, which is a straight line parallel to y-axis. So this is your x equal to mx line. If they are not dependent, if they're independent. Now, let us explain least square regression curves and the principle of least square. So, let xy be a two-dimensional random variable and let y equal to gx semicolon c0, c1, etc. ck be a family of curves. You know that if you are talking about a curve, there are some parameters involved in the curve. So it's a family of curves and c0, c1, ck being parameters. The principle of least square consists in finding c0, c1, etc. ck for which s equal to e expectation of curly bracket y minus gx c0, c1, etc. ck curly bracket square is minimum. So what is the concept behind principle of least square? So principle of least square means you have to find out the parameter c1, c0, c1, ck for which this expression is equal to expectation of e y minus gx c0, c1, ck etc. square is minimum. The squared of the deviation is minimum. Just I explain here. The squared of the deviation is minimum. You have to choose, and that is called the principle of least square. So let us explain if S is minimum, suppose for the values, for some values, and those values are denoted by star. Suppose S is minimum for C0 equal to C0 star, C1 equal to C1 star, etc. Ck equal to Ck star. These are the critical points. Then the curve y equal to gx is said to be the best fitting curve of the given family of the distribution. So if you can find the parameters, the value of the parameters in terms of star here, for which S is minimum, then the curve for those values of the parameter is said to be the best fitting curve of the given family to the distribution according to the least square principle. That is the least square principle. And the curve after the substitution of the values of the parameter is called the least square regression curve of y equal to of y on x belonging to the given family. And that will give you the least square regression curve of y on x belonging to the given family. Okay, so that is the principle of least square and the concept of base fitting curve and the least square regression curve of y on x. Now, from the theory of maxima minima, we know that the necessary condition for s to be minimum is that the partial derivatives del s del c not equal to 0, del s del c1 equal to 0, etc., del s del ck equal to 0. These equations are called the normal equations. These equations are called the normal equations. Now, let us explain this theoretical concept of principle of least square for linear regression curve, that is regression line of y on x. So I am considering first the linear regression, but in my video I will give you the hint for the quadratic or non-linear regression also. So let us start with a two-dimensional random variable. Let x comma y be a two-dimensional random variable, and let y equal to bx be a family of straight lines. As we are talking about a linear relationship, the relationship must be linear. So y equal to a plus bx be a family of straight lines where a comma b are parameters. We shall find the base fitting line of this family to the given distribution by the principle of least square. Okay, base fitting line to this family by the principle of least square. So how will you start? You have to write s. Let s equal to y minus expectation of y minus a minus bx whole square, right? So you have to take the square of the deviation. As I explained, this is your line y equal to a plus bx, suppose, and the points are scattered like this. So you have to consider all the deviations, vertical, all the deviations. You consider all the deviations, it can be below, the points can be below also. So all the squares of the deviations. So you see, you are considering y minus a minus bx. That if y minus a minus bx represents the deviation from the line. Okay, clear? So our task is to find the values of a and b for which s is minimum. What is your task? In the principle of least square, your main task is to find out the parameter a and b. So your main task is to find the values of a and b for which s is minimum. So what are the normal equations? Del s del a equal to 0 and del s del b equal to 0. If you apply del s del a equal to 0, that will give you expectation of y minus a minus bx, the simple partial derivative differentiation, and expectation of x times y minus a minus bx equal to 0. So if you expand more, so this can be written as expectation of y minus a minus b expectation of x, right, equal to 0. So you have a plus b mx equal to my. You have to write like this. And in the second case, you can write this. So these are the two normal equations. Normal equations. Similarly, you can get the second part also from this. From here, you can get the second part. So that are actually from the partial differentiation del s del a and del s del b equal to 0. A and b are only two parameters of the distribution. Now solving these two, this you can solve for, this is the simultaneous, you can solve for these two equations. You can get b star equal to this expression, and you know that the numerator is the covariance of xy and the denominator is the sigma square variance of x. So, and again you can apply covariance of xy is uh, applying the formula for covariance. So that will give you rho sigma y by sigma x. Rho sigma y by sigma x. Okay. So actually your covariance is given by, okay, you can write here, your rho is actually, rho is the correlation coefficient, covariance of xy by sigma x sigma y. Okay, so if you apply your, if you replace your covariance by rho sigma x sigma y, it will be rho sigma y by sigma x. That is the relation. So b star is given by this, and a star, by solving a star you will have my minus rho sigma y by sigma x mx. So these are the values of a star b star. For these values of a star b star, a star will be the minimum. So the minimum is given by, if a star is this, then it can be shown that S is greater or equal to a star, because a star is the minimum for all AB. Thus, S is minimum when A equal to A star and B equal to B star. That is the theoretical development and the mathematical also. You can do it if you have a data. If you want to find out the least square line, you have to go through like this. Hence, the regression line of y on x is given by y equal to my. Actually, any equation of any line is given by this. This is the line, regression line actually. Y equal to my b plus beta yx x minus mx, where beta yx is rho sigma y by sigma x, is known as the regression coefficient of y on x. Beta yx is the regression coefficient of y on x. Beta yx is the regression coefficient of y on x. So this is the regression line of y on x, and it is the least regression line. It is the best fitting curve. It is the best fitting curve. So that is how you can find the regression line of y on x. Now, what about the regression line of x on y? Similarly, you can take x equal to c star d star y. So c star is given by this. Similarly, you can go through the similar process, and d star is this. So you have regression coefficient of x and y is given by beta xy rho sigma x by sigma y. This is the beta xy is the regression coefficient of x and y. And similarly, you can write a regression line of x on y. This is the regression line of y on x. So your regression line of x on y will be, you can write similar way, x minus mx, x equal to mx beta xy y minus my, that way. Okay, now also I will explain now some important observations theorem. You can try this theorem. Expectation of y minus a star minus b star x whole square equal to sigma y square into 1 minus rho square, where rho is the correlation coefficient. I can give you hint for that also. Suppose you can start like this. Expectation of, you have, you look at that, you have y minus a star minus b star x. So you write y minus a star minus b star x, right? That means you can write expectation of y. What is your a star? You look at that, you got the values of a star. A star is my, my minus sigma y rho sigma y by sigma x mx. So you write here my plus rho sigma y by sigma x into mx, and b star x. B star, what is your B star? You see your B star is given by rho sigma y by sigma x. Okay, so you can write rho sigma y by sigma x into x times x squared. Okay, now you can write expectation of, you can use this the regression coefficient, and you can incorporate rho, and you can prove that using the covariance formula. What is your covariance formula? Covariance formula is actually rho sigma x sigma y. You can use this relation to prove the theorem. Okay, this is the hint for your proof. So expectation, you can easily show that this is sigma y square equal to into 1 minus rho square. That you can prove easily. Okay, and the similarly the second one, expectation of x minus c square minus d square y whole squared is sigma x squared 1 minus rho square. And another theorem, this is I will show you graphically, demonstrate by graphs. So if rho equal to plus minus 1, that is correlation coefficient is plus 1 or minus 1, then the regression lines coincide. Also y equal to my plus minus sigma y by sigma x, x minus mx. So that is y is a linear function of x in that case. If rho is equal to plus minus 1, then you see that regression line of y on x is given by this relation, the y on x. This is the regression line of y on x. This is the regression line of y on x. So if you substitute rho is equal to plus minus 1, there will be a linear relationship between y and x. So that was the theorem. If rho is equal to plus minus 1, then the regression lines coincide. Also y equal to, this is you can find out y is a linear function of x. So now I will explain some important things. So if rho equal to 0, then the regression line of y on x is y equal to my, and the regression line of x on y is x equal to mx. So if rho equal to 0, that coefficient gone, so you are remain with y equal to my, that is a line parallel to x axis, and regression line of x on y is x equal to mx, that is a line parallel to y axis. For rho greater than 0, both the regression lines have this positive slopes, while for rho less than 0, both the regression lines have negative slopes. Okay, so if the correlation coefficient is greater than 0, both the regression lines have positive slopes. If rho is less than 0, that is negative, regression lines have negative slopes. Now I will explain measures of goodness of fit. So we first notice that a star, that is the minimum value of s. That is given by E expectation of y minus a star minus b star x whole square gives the mean value of the square of the deviation. Actually, a star gives the mean value of the square of the deviation of the random point xy from the regression line y equal to a star b star x measured parallel to y axis. Right? Already I have explained this with a line drawn, and I explained with the graphs. So the goodness of fit, the term goodness of fit, the best fitting line of y equal to a star b star x will be high if a star is low. Correct? And consequently, a star is an inverse measure of goodness of fit of y equal to a star plus b star x. It is an inverse measure because goodness of fit will be high if A star is low, and goodness of fit will be low if A star is high. So it is an inverse measure of goodness of fit of y equal to A star plus B star x. Similarly, S1 star, that is for expectation of x minus C star minus D star y, that is a regression coefficient, a regression line of y x on y, is an inverse measure of goodness of fit for the regression line x equal to C star plus D star y. Inverse measure of goodness of fit for another line, that is an x on y. So now we know that also from this theorem, the previous theorem, look at the result. Yeah, this theorem, this is a very important theorem for interpretation. I want to interpret the result. So you see, sigma y square is 1 minus rho square, and expectation of y minus a star minus b star x whole square is equal to sigma square into 1 minus rho square, and expectation of x minus c star minus d star y whole square is sigma x square 1 minus rho square. Therefore, a star and s1 star both become low if the value of mod rho is high, because this expression depends on rho. So A star and S1 star both become low if the value of mod rho is high. And for low values of mod rho, we get high values of A star and S1 star. Okay? Because that directly depends on rho, correlation coefficient. In other words, mod rho is a measure of concentration of the probability mass about the regression lines. So mod rho is a measure of concentration of the probability mass about the regression lines. Okay? And mod rho is very satisfactory measure of goodness of fit of the regression lines to the bivariate distribution, because it is dimensionless and independent of the choice of origins and scales of measurement. So what is your so this is about your measure of goodness of fit. Finally, so in this we have learned about the different regression curves of y on x and regression curves on x on y, and also about the idea how to calculate the measure of goodness of fit. So mod rho, it depends, measure of goodness of fit depends on the mod rho. So if mod rho is a direct measure of goodness of fit. Now let us explain with some diagram. So look at that. If rho is greater than 0, if rho is positive, then you have a positive slope for both the lines for a bivariate distribution. Both the lines, positive slopes. And this point of intersection is called the mx, my, that is mean of x and mean of y. They will intersect at mean of x and mean of y. So this is positively correlated. Then both the regression lines have positive slopes, and their equations indicate that it is most likely to get the relation between x and y. That is, if y increases as x increases. That is the significance. Next one is rho less than 0. So both the lines have negative slopes. And it is most likely to get the relation between x1, x and y as y decreases as x increases. It means y decreases as x increases. And this is your rho equal to 1. If rho equal to 1, already I explained. You look at that. I explained in the previous theorem, if rho equal to 1, then the regression lines coincide. And you get a linear relationship between y and x. Y is a linear function of x. So that is how. Directly related to, if rho equal to 1, you have a direct relationship between y and x. Linear relationship. And the two lines coincide. And for rho equal to -1, negative slope, again the two lines coincide and you have a linear relationship between y and x. This is your rho equal to 0. So rho equal to 0 means no correlation, uncorrelated. So there is a least possible concentration of the probability mass near the regression lines y equal to my. So this is your y equal to my line that is parallel to x-axis, and this is your x equal to mx line that is parallel to x-axis, parallel to y-axis, sorry. So this is your regression line of x and y, and their point of intersection is mx, my. So rho equal to 0, no correlation between them. And also for curve fitting, I will give you the idea of the parabolic curve fitting, that is the non-linear. So how will you start with the non-linear? So definitely I will give you the idea about the non-linear. Just for non-linear, x comma y is a bivariate distribution. It's a two-dimensional random variable. And for non-linear or parabolic, you can consider the polynomial as c1 plus c0 plus c1x plus c2x squared, etc., and plus ck x to the power k, right? And where c0, c1, c2, ck are parameters, okay? And you have to consider the s, the best fitting line of this family to the given distribution by the principle of least square we shall have to find. So you have to consider, let s equal to expectation of y minus c0 minus c1 x minus c2 x squared minus etc. ck x to the power, okay, x to the power k whole square. Okay, this is your s star. Now we have to find out the values of c0, c1. Actually we have to find out the values of c1, that is c0 star, c1, that is c1 star, etc., right? These are the values for which s should be minimum. And you have to consider the normal equation as del s del c0 del a equal to 0. These are the normal equation. Del s del c1 equal to 0, and so on, right? And in this case also you can explain the goodness of fit also. So for goodness of fit, in this case also you can measure the goodness of fit for the parabola. So if rho is, value of rho is low, then a star is high, and value of rho is high, a star will be minimum or low. So A star is the measure of goodness, rho is the measure of goodness of fit. Let me go to that portion. So this A star, so if rho is high, A star will be low. Okay. Oh, and if rho is low, A star will be high. So that gives you the rho, mod rho direct measure of goodness of fit in the parabolic curve fit. In nonlinear also you can measure. So this is the concept of polynomial curve fitting. Okay. So in that way you can generalize the concept. So we discuss in this lecture the regression line, especially regression curves, how to draw the regression curves and what is the physical interpretation, and a linear regression line, base fitting line, and also some hint for how to draw the concept of non-linear curve fitting or parabolic curve fitting. Okay, thank you all of you.